Okay, so for the first part of homework 3-4 here. Question 1, in order to get an object moving, you must push harder than it pushes back on you. Hopefully we all saw through that pretty quickly, but that is false, right? We know that anytime we exert a force, there is always an equal and opposite force. So no matter how hard you push, the object will always push back on you equally hard. So it's not possible for us to push harder than it pushes back on us. In order for it to move, our push must simply be more than the frictional force or whatever forces are holding it in place. But that is a false statement, right? Again, always equal and opposite, so you cannot push harder than something pushes back on you. Question 2 here, very similar to a couple questions we've seen in both homework and notes before. So this rope here, which has an object just hanging, and it does tell me all three of these are at rest, so both of these systems are at rest. So if this object is hanging, right, then I know that the force of gravity pulling down would be equal to the tension pulling up. Similarly, for these two, right, if I focus on them one at a time, the force of gravity pulling down on this one, because it's not moving, has to be equal and opposite to the tension that's pulling up. And just like that for the third block over here, again, that tension pulling up has to be equal and opposite to that force of gravity pulling down. So if you take this one block at a time, it's very clear to see that this tension over here has to be equal to the force of gravity, this tension over here has to be equal to the force of gravity, and because they're the same mass, they have the same force of gravity, and therefore their tensions would be the same, right? The misconception to watch out for here is just because you have two masses instead of one, that does not automatically double the tension, right? The system is still at rest, so if I focus on one object at a time, it's very clear to see that this tension only needs to match the force of gravity of either one of these to maintain that balance. It does not have to match both of them. And then question 3 here on multiple choice, very similar again to questions we've seen before, and really even the last two that we've seen, right? So a small car is pushing a larger truck that has a dead battery. The mass of the truck is much larger than the mass of the car, which the following is a true statement. Well, again, the mass of the objects doesn't make any difference. If we're considering the forces which each of these is doing, we know that the force is always equal and opposite. So the car exerts the same amount of force on the truck as the truck exerts on the car, right? Again, don't be thrown off by the masses. Yes, their accelerations may be different because their masses are different, but the forces are always in equal and opposite action-reactions. So really, all of these first three questions were example of Newton's third law, right? They were all examples of Newton's third law, which says that all forces exist in pairs, and they must be equal and opposite as they exist. Question 4 here, the key to this question is the fact that it's being pulled upward with a constant velocity. And we know the second we see constant speed, constant velocity, right, we know that means the net force must be 0. So really, if I focus on these two objects individually, well, what that tells me is the tension. So if I focus on this 100 one, right, that would tell me that the tension needs to be equal and opposite to the force of gravity on this first block. So I actually know the tension is 100 newtons if I needed to know that. The tension down here is, tension T is. But they actually just asked me what's the relationship between T and P. Well, because I know it's moving at a constant velocity, if I focus on this block, right, on that 25 Newton block, well, I've got tension P pulling upward. I have both tension T and the force due to gravity, which I know is 25 newtons pulling downward. And again, because it's moving at a constant velocity, I know the net force is 0. And therefore, all of these add up to be 0, which tells me, more importantly, that P is equal and opposite to T plus 25 newtons, right? So again, because it's a constant speed, I know that my tension up here is equal and opposite to those two. If it was accelerating upward, right, that would tell me that P has to be more than these two combined, right? If it was accelerating downward, then P would have to be less than those two combined. So make sure you're pretty comfortable on those types of relationships, but hopefully none of these first 4 multiple choice questions was too difficult. Okay, so for question 5 here, rather than have you guys watch me struggle as I attempt to write this out, I went ahead and just typed it out. But will the hanging magnet in front of the car, cause it to move forward? Well, the answer to that is no, right? Otherwise, why wouldn't we just do this, right, in some form or fashion rather than using gasoline and whatnot, right? So the reason that it's a no is it's simply an extension of Newton's third law, right? Yes, the magnet does pull on the cart, right? So the magnet does exert a force on the cart. However, that force does not exist on its own, right? All forces come in equal and opposite pairs. So as the magnet pulls on the cart with a certain force, the cart then pulls back on the magnet with that same force, that same magnitude, in the opposite direction, right? So then the net force on the entire system would be 0. The other way to think about that is these two forces are internal to the system, right? They're not external forces on the system. They are within the system itself, the system being the cart and the magnet. And any forces within a system, any internal forces, are not going to cause any change in motion of the system. The only way to cause a change in motion of the system would be to have an external force. So a force that's not part of this setup here would have to act on either the cart or the magnet or both. But in this case, again, here's kind of the explanation I would go with, or the explanation of it's not internal, or these, are internal to the system, and it requires an external force to cause a change in motion or an acceleration. So anyway, this does not happen again. Otherwise, why wouldn't we just do this to cause cars to accelerate? But anyway, so question 6 here, I tried to mess with you a little bit just to make sure we are thinking about it. So we've got the two 5 kilograms blocks, but I did say that the system is not at rest. The masses are not at rest. However, they are both 5 kilogram blocks, which means if I think about this, just because it's not at rest doesn't mean the net force isn't 0, right? In this particular instance, yes, they are moving upward, but they actually are moving upward, or in this case, the right-hand side is moving downward with a constant velocity. And so because they're moving, but they're moving at a constant velocity, I still know that my net force is 0, which is very, very important, because if my net force is 0, then if I think about either object, so I'm going to call this object 1, this object 2, and then I've got my spring in here as well, right? So if I focus on object 1, right, well, the forces that act directly on object 1 would be its force of gravity pulling down and tension pulling up. Again, even though the system is moving, right, it doesn't have a net force because those two masses are equal, and therefore I know that the tension is equal to the force due to gravity. Well, then if I extend the tension over the spring here, so now if I focus on the spring, right, well, here I've got my spring. I know the tension is pulling upward on that spring, which means the spring force better be pulling downward, equal and opposite to that, because again, it's part of the system and it's moving at a constant velocity, right? Similarly, on the other end of the spring, as the spring stretches one way and pulls down, the spring is just like a rope in the sense that as that spring pulls downward on one of those ropes, the spring is also going to pull with that same force upward on the other end of the rope. So imagine that spring continuing on down here. So that spring force is pulling upward with that same force, and then that tension in that rope would have to be the same as well, because that tension in that rope needs to match the force due to gravity of my second object over there as well, right? So all of this, everything here is still in equilibrium. It's just in dynamic equilibrium, which is equilibrium in motion, as opposed to static equilibrium. But don't let me throw you off by that, right? The spring force would still have to be equal and opposite to the force of gravity, right? Through the tension here, it'd have to be equal and opposite to the force of gravity. So anyway, they asked me to find what is the Newton scale reading. Well, the spring force is equal to the force of gravity, so all I need to know is what's the force of gravity of either of those objects, not both of them together, but either one individually. And in this case, it's a simple application of the 5 rule. So 49 newtons equals the spring force, and I'm done, right? So very similar to those questions we've seen earlier, where maybe you have two masses that are hanging, and then there's a spring scale on the table. It's really the exact same concept there. The idea that I want you to extend it to is just because the system's not at rest does not mean it's not in equilibrium. So as long as you're pretty comfortable with that, this question was not too tricky. Hopefully question 7 wasn't too tricky either. However, this one maybe is a little bit counterintuitive, right? Because at first glance you think, well, I've got a 10 Newton weight over here and I've got a 10 Newton force, so they're both going to accelerate at the same rate. However, that's not the case. And the reason for that is, if I look at this here, right? Well, if I look at this here, I know that the net force would come from the force of gravity, which is 10 newtons, minus the tension, right? So the net force, the force of gravity of this block minus the tension. But if that's the net force, so if the net force equals the force of gravity minus something, And that tension is definitely not 0 because we've got another mass up here. So if I'm taking the force of gravity and subtracting something, doesn't that guarantee that my net force has to be less than 10? Right? Because I'm taking 10 newtons minus something. Whereas over here, I'm not looking at my net force, I'm simply applying a constant force of 10 newtons to that rope. So in this case, the tension, I'm saying right here, the tension is 10 newtons, and that tension is exerted all the way through. So in first instance up here, again, the tension would be something that is less than 10 newtons, whereas in my second diagram, the tension would be 10 newtons exactly, right? So again, the tension up here, less than 10 newtons, the tension over here is equal to 10 newtons. And so what that tells me then is case B is going to have a higher acceleration. So is block A's acceleration in case B greater than, less than, or equal to case A? Well, it's greater than, right? Correct answer again is greater than. Because I know that I've got a stronger overall tension and overall force acting on block A in case B as opposed to case A. So anyway, hopefully this made sense. If you do have any questions on this, let me know. I know these questions can be tricky, but hopefully it's not too bad with a little bit of explanation with it. So then question 8 here, right? Question 8, kind of a different setup than we're used to, but still not too bad. The biggest key is the fact that because the springs, or excuse me, the string and the pulleys are all massless and frictionless, the tension is the same everywhere in that string. And that's very, very important because obviously if I think about this system, so if I just kind of stop for a second and think about it, right? I know that block B is not going to move upward, right? Block B, the net force acting on block B is going to have to be going downward because that block is either going to fall or it's not going to do anything. But since there's no friction on the table, I know that block B in fact will fall down, right? So if I focus in on block B, I've got a force of gravity pulling down, I have a tension pulling upward. I know the net force on block B would come from the force of gravity on block B minus the tension, right? The same way that we would normally approach this problem. Okay, so that's nothing too crazy. And then I get to block A. Well, when I focus on block A, the trick here is you have tension pulling throughout that string, and so you really kind of double up the tension. By having that pulley on block A, I have a tension that's pulling on this end of the rope, and I have an equal tension that's pulling on the other side of that pulley, on the other side of the rope. So anyway, if I look on block A, if I look at block A here, then the net force obviously is going to be going to the right, and the only thing providing the net force are those two tensions, right? That same tension, but it's doubling up. So then the net force on block A comes from 2 times the tension. So I've got these two equations to work with. I've got FB equals FGB, the force of gravity acting on that block, minus tension. And then I have my net force on block A coming from 2 times the tension. So at this point you could do any number of things. You could definitely do substitution, which might be easier. You could still do elimination method as well, which I actually will do. The only trick I would have to do first is I'd have to multiply this equation by 2 so that my tension, which I don't know, ends up canceling out. So I'm actually going to multiply that top equation by 2. So this would be 2 times the net force on object B equals 2 times the force of gravity of object B minus 2 times the tension. And again, that allows me to use elimination, right? So then I can add these two equations up. I get the net force on object A plus 2 times the net force on object B equals 2 times the force of gravity of object B, and then my tensions conveniently cancel out, right? Again, not the only way to do it. You could have also used substitution. You should have got an equivalent mathematical expression. At this point, though, all I have to do then is plug in the values that I know. Well, mass A I actually know, times the acceleration of the system, which is what I'm looking for, right? Plus 2 times mass B, which I know, times the acceleration of the system, equals 2 times mass B, which I know, times gravity, which obviously I know. So again, at this stage, all it is it's a matter of plugging everything in. Well, mass A is 4, so I have 4A plus 2 times my mass B, which is 5. So I've got 4A plus 10A equals 2 times, again, 5 times 9.8. Well, this is actually, most of this is math that's easy enough. We can do it in our heads, hopefully, right? So on the left-hand side, I get 14A. On the right-hand side, I get 10 times 9.8, so 98 newtons. So then solving for A, I just divide both sides by 14, and I get 7 meters per second squared. So block A and block B both accelerate with an acceleration of 7 meters per second.